Let's find the Fourier transform of step signal, and for this we will consider the time domain signal xt equal to unit step signal ut, and we know ut is equal to 0 when t is negative, and we know it is equal to 1 when t is positive, and we are interested in calculating the Fourier transform, let's call it x omega, of the unit step signal. And for this we will first find whether ut is absolutely integrable or not, because we can use the formula of Fourier transform only when ut is absolutely integrable. And for this we will use the waveform of ut. You can see ut is having the value equal to 0 from minus infinity to 0, and it is having the value equal to plus 1 from 0 to infinity. So it implies magnitude of ut or mod ut will have the same waveform as ut. Now we will check the condition for a signal to be absolutely integrable, and for this we will calculate the integration of mod ut from minus infinity to infinity with respect to t, and after calculation you will find it is equal to infinity. So here the condition for a signal to be absolutely integrable is violated, because this result should be less than infinity, but here we are having the result equal to infinity, and this is happening because ut is non-converging. It is having a constant value from 0 to infinity, so the waveform is non-converging, and therefore we cannot use the formula of Fourier transform to calculate the Fourier transform of ut. And if we want to use the formula of Fourier transform, it is important to make ut converging. So if we can make ut converging like this, we can use the formula of Fourier transform, and the equation for this converging waveform we can write as e power minus at ut. So we can write ut as the limiting case of e power minus at ut. We can write ut equal to e power minus at multiplied to ut if a is tending to 0. So we will write limit a tends to 0 e power minus at ut equal to ut, and here we can apply the Fourier transform on both the sides, and we can have the Fourier transform of ut. But this process is little bit lengthy and complicated, so we will not use this process to calculate the Fourier transform. Instead we will use the Fourier transform of Signum function. In the last lecture we obtained the Fourier transform of Signum function, and it is equal to 2 over j omega. So if we represent the unit step signal ut in terms of Signum function, we can easily obtain the Fourier transform of ut. And for this purpose I will compare the waveform of Signum function with the waveform of ut. And after comparison you can see there is one difference between the two waveforms. Signum function is equal to minus 1 from minus infinity to 0, but ut is equal to 0 from minus infinity to 0, and from 0 to infinity the two functions or signals are same. So in order to write ut in terms of Signum function, it is important to make minus 1 equal to 0, and we can do this by adding 1. So we will perform the amplitude shifting. We will add 1 to the Signum function, and after doing this we will have the waveform like this. From 0 to infinity Signum function was equal to 1, and as 1 is added we will have 2 from 0 to infinity, and from minus infinity to 0 Signum function was equal to minus 1, and after adding 1 we will have 0 from minus infinity to 0. But still this waveform is not the waveform of ut, because ut should have 1 as the value from 0 to infinity. That's why we call it unit step function. Here we are having the step function, but it is not a unit step function, it is 2ut. So to get ut we will divide both the sides by 2. So we will again perform the amplitude shifting, and we will divide 1 plus Signum t by 2, and this will give us the waveform of unit step signal like this. So we can write ut is equal to 1 plus Signum function divided by 2, or we can write ut is equal to 1 over 2 plus 1 over 2 Signum function. And now we will take the Fourier transform on both the sides. So we have Fourier transform of unit step signal equal to Fourier transform of DC value 1 over 2 plus 1 over 2 multiplied to Fourier transform of Signum function. Now it is very easy to calculate the Fourier transform of DC value and Signum function, and the Fourier transform of ut we have assumed as x omega. So x omega is equal to 2 pi multiplied to 1 over 2 multiplied to delta omega, because we know the Fourier transform of DC value a naught is equal to 2 pi a naught delta omega. Here a naught is equal to 1 by 2, so here we will have 1 by 2. After this we will write the Fourier transform of Signum function. It is equal to 2 over j omega, so 1 by 2 multiplied to 2 over j omega. This 2 and 2 will cancel out, this 2 and 2 will cancel out. So finally x omega is equal to pi delta omega plus 1 over j omega, 1 over j omega. So this is the Fourier transform of unit step signal. Ut is having the Fourier transform pi delta omega plus 1 over j omega. So remember this result, it is very useful.